Oh, so this is 8.4, lesson on partial fractions. That's probably all I'll record, and then I'll do a different one for the rest of it. So if I have 2x plus 5 over x squared minus x minus 12 dx, if you wanted to, you could do a u substitution. That would be possible. You'd get 2x minus 1 as your derivative of u, assuming this is your u, and the 2x works pretty well, but the minus 1 isn't as nice because I have a 2x plus 5. You could work around that, but it'd be easier to just rewrite this using partial fractions. So just looking at 2x plus 5 over x squared minus x minus 12. First thing you want to do is factor the bottom, x minus 4, x plus 3. And then we can rewrite this as a over one of the factors and b over the other factor. And then we can multiply both sides by this red amount. So multiply x minus 4 times x plus 3 times both sides, and on the left those will cross off, so you just have 2x plus 5 equals a, and these x minus 4s will cross off, so I have x plus 3 plus b, and then these x plus 3s cross off, times x minus 4. So I get 2x plus 5 equals ax plus 3a plus bx minus 4b. And then we can set up a system of equations where you have one for the x and another one for the constant. So how many x's do I have on the left side? I have 2. And how many x's do I have on the right side? I have a plus b. And as far as constants goes, I have 5 on the left, and I have 3a minus 4b on the right. So we have a system of equations. We could use a matrix if we were lazy and wanted to use our calculators. I'm going to just remind you how to do that, because they aren't all going to be 2 by 3. So I'd first write it as a plus b equals 2. 3a minus 4b equals 5. Think of it that way. So it'd be 1, 1, 2, 3, negative 4, 5. There's my 2 by 3 matrix. Matrix edit 2 by 3, 1, 1, 2, 3, negative 4, 5. Math, reduce row echelon form. I didn't clear out of there. So matrix, really, matrix, math, reduced row echelon form. I'm having a hard time. I think you could conclude that it would have been a lot easier to use substitution or elimination at this point. So reduced row echelon of matrix A, and I probably butchered matrix A the last. 1, 1, 2, 3, negative 4, 5. Ooh, okay, so I guess that was right. And I could maybe hit math, enter, enter, and change it to fractions. So A is 13/7 and B is 1/7. An example of where technology really didn't save us much time. So our integral, that's our A and B, so our new integral is going to be We're going to rewrite it with on the right, except we're going to have our new a and b. So it's going to integral of 13/7, 1/7, so this 13/7, so I'm going to do integral of 13/7 times 1 over x minus 4. So this can go up front, so it's 13/7 natural log absolute value of x minus 4 plus 1/7 natural log absolute value of x plus 3 plus c. One problem done. So that's using partial fractions. Questions on the first problem? There's other exceptions to the partial fractions that I'm going to talk about. Alright, so just factor the bottom, put a over one factor, b over the other factor, multiply both sides by that bottom, and go from there. Alright, segue. What if we have integral of x cubed minus 4x squared on the bottom, dx. Alright, so for this one, you can see that we have x squared plus 2x minus 3, and I can pull out an x squared here. It's x squared times x minus 4. So this is another partial, not that you can see it, another partial fraction problem. But since we have something being squared or cubed, you have to assign a for the x squared, and you have to assign b for the x, and then finally c for x minus 4. So if it was like x squared plus 2x minus 3 over x cubed times x minus 4, it would be a over the x cubed, b over the x squared, c over the x, and then d over x minus 4. So if it's multiplicity 3, you need to do a letter for each one. Multiplicity 2, you have to assign a letter all the way down to the first power. So then you would multiply both sides by the bottom here, set up a system. The system would be a 3 by 4 system probably, and actually a matrix might be a good idea to do that. Okay, I'm not going to actually integrate that. I'm not even going to go any further with this partial fractions unless you want me to. I don't know how much you remember. We did do this stuff.
Yeah, how do you get from like that step to like the step, like the next step?
The next step? Okay. So you're good up to this point. I'll do this top one because that one's going to be a lot of work. So you're going to multiply x squared times x minus 4 both sides. So these will cross off on the left. So I have x squared plus 2x minus 3 equals. Now we're going to distribute it to each of these. So these x squareds are going to cross off for this one. So it'll be a times x minus 4. Camera. There you go. So it'll be a times x minus 4 plus, and then just if you distribute this to this x, and one of those x's is going to cross off. So it'll be bx x minus 4 plus, and then the x minus 4's are going to cross off with the c one, so it'll be cx squared. So just cleaning it up, ax minus 4x squared minus 4bx plus cx squared. Our system will have an equation for the x squareds, for the x's, and the numbers. So x squared, we have 1 on the left, and we have b plus c. For x's, I have 2 on the left, and I have a minus 4b. And numbers, I have negative 3 equals negative 4a. So you can do a matrix with that, or just see that a is 3/4 by dividing by negative 4. Plug that in, get b, and plug that in, you get c. And then usually the antiderivatives are pretty straightforward, but not always. Like, you could do all that and then you still have some more work to do once you create your new integral. Another type of problem that you'll see if we're integrating I'll just do that, x cubed plus 10x. Okay, so we factor the bottom. It's x times x squared plus 10, and we can't factor any longer. You can't factor any more than that. So we put an a over the x, and since it's a non-factorable quadratic on the bottom, x squared plus 10, we can't factor it. It'll be a bx plus c over x squared plus 10. And if you put this one first, it would just be an ax plus b and then c over x, but you're going to get the same answer. It doesn't matter. So if it's a non-factorable quadratic, you put bx plus c on top and go from there. I think there are problems like that in your assignment. So all of these have not been, the fractions themselves have not been improper, but if you have something like 4x cubed minus 6x squared plus 4x minus 1 over 2x squared plus, I don't know, x minus 2. So if you have this, the first thing you have to do is you have to divide the bottom into the top. Even if they're the same degree, you have to divide that in. So this is 1 degree bigger, but if they're the same, you still would have to divide. So in this case, we can't even use synthetic division. You'd have to use polynomial division to start with and get some answer. And remember, we're integrating all of this stuff, so all we're doing now is rewriting this a different way. I suppose I could do this. Why did I pick such big numbers? Okay, so 2x goes in there. 2x times 4x cubed plus 4x squared minus 4x. Subtract negative 10x squared plus 8x minus 1 minus 5. So gone 13x minus 11 over 2x squared plus x minus 2. Okay, so that's our new one. We'd integrate that and get x squared, integrate that, get minus 5x. Then we've got another one to integrate that may actually need to use partial fractions. So you'd just be starting the problem with partial fractions once you get to this point. Alright, so questions on this stuff? This is just partial fractions right now.
Wait, where did the 4x
right there. The 4x
Yeah, right
cubed.
there.
Yeah, that should be 2x squared, huh?
Okay.
Good call. Thank you. So that'll mess, but that that's how you would do it if I knew how to multiply. Any other questions on that stuff?
Because I did not pay attention in Mr. Frisbee's class in 10th grade. If you had like, so we're the top of we can see and it's x squared plus 10. If it was like x cubed plus 10, would that be bx squared?
It would be. Yeah,
Okay.
you've never been asked to do that, but it's always 1 degree. Good question. But you've never been asked to do that. Okay, so I'm going to stop it there.